So hello everyone. So today we're going to talk on the column space. In the previous tutorial we have started with introduction to the vectors, and we will continue with this session with the same introduction part. And today we are going to talk about what is the column space, how do we define it. So basically, as we all know, that any matrix can be represented in a form of Ax equal to B. So our right hand part is equal to B. It means a matrix A contains the coefficients, and x times the coefficient of matrix A should be equal to B. It means we have to solve this equation here. We have to find the unknowns, that is x here. So now we are trying to represent these matrix and the unknowns in a form of the column space. For example, if we have any matrix here, for example, let us take a simple matrix that is 2 1 minus 1 and 4 2 then 1 and 3 1 and 2. So these are my coefficients which represents the matrix A, and it means now we have the may not be necessary always. So let us consider the three unknowns, that is x1, x2 and x3. So then this should be equal to, say, sum of the right hand side of the equation, maybe minus 1, 4 and 5. So this can also be written in a form of a column space or a column vector, like this can be written as, that is x1 into, that is the first column of this matrix is 2 4 3, and the plus, this can be written as plus x2 into the second column, we can write this as 1 2 and 1, and the third column we can write this as with x3 times the column 3, that is minus 1 1 2, and this should be equal to our right hand side of the equation, so that should be like minus 1 4 and 5. So if we can write this, and all these column vectors are in some space or in some plane, then this vector B should also be in the same plane. So then we can solve this, that is Ax equal to B, we can solve this equation. If it is not in the same plane, then we cannot solve this equation. So that is what this definition it means. So let us look into the definition here. The column space consists of all linear combinations of columns. The combinations are all possible vectors Ax. So they fill the column space, and that is called as C of A. So now to find the solution, so the condition is that, so to solve Ax equal to B is to express B as a combination of columns. So then the right side B has to be in the column space produced by A on the left side, or no solution. So let us write this. So the system Ax equal to B is solvable if and only if B is in the column space of A. So just now we are told that we have taken one example here. So now if we write these into some plane or the space, so all these are A columns. So if there is if all these A columns are in some space, so then B should also be in the same space. If it is not in the same space, then we cannot find the solution for this. So that is what it means. So that is the definition of this one. And if we consider that the A is a matrix of dimensions, say m cross n, then the column space consists of the column space A will be a subspace of r power m. So it means how many components are here? If you look into this equation, so there are 3 rows. It means if you look into the vector space here, so this vector space consists of 3 components. So now it is in a 3-dimensional plane, that means it is defined as r power m, not r power n. For example, what do you mean by r power m? So it is not necessary to have three components, it can have two components as well. Here, rather than a square matrix, it can be a rectangular matrix as well. So now we have here the uh, three columns, but we have the three unknowns. This we'll talk about this later, how we can write this. There is something called the free variable, so there we will talk about, or echelon matrix, so there we will talk about these free variables. So now it is something like this. So when we solve this, so we have the pivots over the diagonals, maybe we will get the pivots over the diagonals, and then whereas the last column here is not in a diagonal form, so it will not come in the diagonal of pivot, so that will become a free variable. So now it is of the if you look into the components here, if I erase this, then we have only two components. So now it is the matrix A, rather than it is 3 cross 3, now this matrix A is equal to 2 cross 3 matrix. Now its column space will be defined in terms of R square, whereas in the previous case it was defined as R power 3. It means it's a 3 dimension. Now here it is represented with 2 dimensions because we are representing the column space. So the column space A is a subspace. So column space A is a subspace of R square in the second case. So let us look into one example here. So we have taken one example. So let us take one more example here to better understand. So let me save this page. So let's take an example here as AX equal to, that is we have 1 0 4 3 2 and 3, which is of x1 x1 x2. So this can be written in the form of a column space, so like this, that is x1. So all this column space should also satisfy the two rules, that is I have not defined it. So the two rules is that is v plus w, it should be in the same space, and c into v should also be in the same space. It means when we add the two column vectors, it should be in the same space, column space, whereas if you multiply by a scalar, if you multiply a vector by a scalar, that is the second rule, it should also result in the same space, same column space. So then it means it satisfies both the rules, so then we have no problem. So let us come back to this example here. So x1 is the first column, so x1 times the first column plus x2 into 0 3 3. So now this should be equal to our b. So now this can be defined, the plane, if you write here, so then if you have a plane here, something like this, the three-dimensional plane, so then this vector 0 3 3 will come here somewhere. So if you define this three dimension, and b will be in the same plane here, and this 1 4 2 is also in the same plane here with the vector. So here somewhere it will come 1 4 2. So 1 4 and 2, and 0 0 0 it is comes here. So if we write the plane here, for example, the plane is something like this, a tilted plane. So the b and this the first column and the second column vectors or lies in the same space of this column space, that is a subspace of r square. This is now subspace of r power 3 because we have 3 components in the vector column. So now if, we'll look into a few other important things here, the different notations of representation. So instead of column in R power m, we could start with any set S of vector. So we can call this as set S of the vector in the vector space V, and we also call SS as the subset of set S. So let us define that. So we have S here, which is the set of vector in V, and the subset is all combinations of vectors in S. So then SS can be defined as something like this. Then SS is equal to all, that is C1 into V1 plus C2 into V2 plus dash dash up to Cn into Vn, which is equal to the subspace, which is equal to the subspace of V spanned by S, which is nothing but it is the subspace. So all these are the subspace of V spanned by, span means it exists in the S. So S is the set of columns and SS is the column space. So where there are only one non-zero vector in V in S, the subspace SS is the line through V. So that's what. So and always SS is the smallest subspace containing S. So these are the few definitions of the space and the subspaces. So I'll repeat again. So always the SS is the smallest subspace containing S. So let us take one example here that we have defined. So let us take an identity matrix. It is 1 0 2 cross 2 identity matrix here, and we have A as 1 2 2 4, and we have a B which is equal to 1 0 2 0 and 3 4. So identity matrix is the whole space here with whole space that is represented as R square, and the column space of A is only a line. If you look into the second column, that is 2 and 4, it is a multiple of the first column, that is 1 and 2. If you multiply the first column by 2, then we will get a resultant column, one more column, that is 2 and 4. So those vectors are different but still lies in the same vector space. So that is the way of defining it. So next we'll talk about the null space, which is important. So far we have considered that Ax is equal to B. So next we will consider the null space. We are talking when the right side of this equation which is equal to 0. So let me clear this everything. So previously what we have written is that we have that Ax equal to B. So it depends. If A is invertible, we may have some solutions or we may have many solutions. But here the right hand side of the equation, so most of the times it may happen that the right side of the equation which is equal to 0. So now we will see what is the null space. So now for here we have m by n matrix that is defined by A. It may be a square matrix or it may be a rectangular matrix, and one immediate solution is that we can define the x is equal to 0, and for invertible matrix this is only one solution. So now let us write the definition of the null space here. So the null space of A consists of all solutions to Ax equal to 0. So these vectors x are in R power n, and the null space containing all solutions of Ax equal to 0 is denoted by n of A. So the null space of A consists of all solutions to Ax equal to 0, and these vectors are represented as A power n. So if I erase this, let me write this as properly, this R power n. So R power n, the null space containing all solutions to Ax is denoted by n of A. So to understand this, we straight away look into an example to understand the null space. So let us take an example here. So we'll take this x plus 2y plus 3z is equal to 0. Comes from the matrix 1 cross. Now if you write these in terms of matrix, then we have the A as the coefficients here for this equation, that is 1, 2 and 3. So it is a 1 cross 3 matrix, and this matrix is a form that is Ax is equal to 0, and this will produce a plane through the origin that is 0, 0, 0, and the plane of the subspace is, because it has the 3 components, if we the plane, if you go to the plane as the row, so then it is R power 3, it is the null space of A. So if we redefine the same equation with right side, rather than 0, if we define it as 6, then also forms a plane but not the same subspace. So probably this may not be that clear to understand, so we will go with one more example to understand. So let us take one more example here. So for example, we have x1 is equal to 2x2 equals 0, and 3x1 plus 6x2 is equal to 0. So now we can write this in a form of matrix as well. So if I write this here, so 1, 2, 3 and 6, and the right side is 0, so we have we'll define it as x1 and x2, then which is equal to 0. So now if we go with the elimination process as usual, so how do we go for elimination process of this matrix is that we'll multiply the first row by 3 and subtract with row 2. So then I'll get this as 1, 2. So this is a 3, I'll get 3, I'll get 0 here, and this is 3 to the 6, I'll get 0 here. So this is nothing but we got by subtracting 3 times row 1 to the row 2. So we got this matrix. So now if you look into this matrix, So what are the possible solutions that we have? Means that the line in the null space, what is the null space here consist of, and what is the special solution that exists? So now if you write this in this form as a vector, so sorry. So now the second, if you look into the second row has completely become 0, so there is no point of writing. Therefore I can write this as x1 plus 2 x2, which is equal to 0. So now this second pivot, the first pivot is 1, fine, but the second pivot here it is 0, so there is no pivot. So what happens is that, so this column here, so it has become a free column. It means I can substitute any value to this x2. So any value to this x2 is that I'll just substitute x2 is equal to 1. So let us substitute x2 is equal to 1. Then what happens to this x1? So this x1 will value becomes minus 2. So because I substituted, when I take it to the right side, so this I'll get it as 1. So the null space of A, so if you write the null space of A with 1, 2, 3, 6, then contains a multiples of S, multiples of the special cases. So special case, it consists that, what are the special cases that it consists? Now what is its x1? So from this we got x1 as minus 2. So let us write, and what is, what is that x1 we got? We got minus 2, and what is x1? And x1 we got it as 1. So this is the special case, one of the special case. Okay, and there might be another solution also exists, the special solution. If I substitute x2 is equal to 0, then what happens? Then the other special solution I may get here it as the completely 0, so which may not be a feasible solution. So if I substitute x2 is equal to 0, then I'll get x1 is also 0 and x2 is also 0. This is not a solution at all. So whereas this condition is fine here. So I'll repeat once again. So we have a matrix here. We have taken a equation, a linear equation here. We have two equations and we represent that in a matrix. And this matrix A we have reduced, we have come to an elimination matrix by same process which we are used to do it before, that is multiply 3 times multiplier here, that is the value of L is equal to 3. So 3 times the row 1 subtract with the row 2. So then what happens is that, so even here we don't get any second pivot. The second pivot will become 0. So it means we have only one pivot here, that is 1. So this has become free matrix. So there is no significance of second row here. So then we can write the first row as again equation, that is x1 plus 2x2, which is equal to 0. So then this x2 has become the free variable. Why? Because here it has no pivot here. So it can substitute x2 equal to 1. Then we can find a special space that is minus 2 and 1. So now now the null space consists this S is equal to minus 2 and 1. So the best way to describe the null space by computing the special solutions to Ax equal to 0. Likewise, if you consider just take one more example here with 3 unknowns with one row, then if I write here again, what happens is that, so let us take this 1, 2 and 3, and this is x, y and z. We have 3 unknowns which is equal to 0. So now if you look at once again, so we will get different solutions for this case. Why? Because here its pivots for the second and third pivot are 0. If we write this diagonal matrix here, so there is only one pivot, that is 1, that is the first pivot. Second and third pivot are not there. So what happens? These two columns, the second and third column will become the free variables. Now I can substitute. So if I write these in terms of equation, so I'll get something like this, that is x plus uh, x plus 2y plus 3z, which is equal to 0. So now I can substitute any value for z as well as for y. So better is always represented these values in terms of 0 or 1. So I'll take first I'll take first z is equal to 1 and y is equal to 0, and we'll see what is the solution we will get. So when I substitute that, then what is the solution that I'll get here? That is s1 is equal to that z. So here this term will become 0. Therefore, what is this value of x that I'll get? So from this I'll get x is equal to minus 3. So now if I write all these values on the right side, so this is my solution now. So I got my unknowns of the x is equal to minus 3, y is 0, and z is 1. So this is one solution. The other solution is that I can write here, so I'll just move this entire thing up. Slightly up. So the other solution is also exists. The other solution is that now in the second case, let us consider z is equal to 0 and we'll consider y is equal to 1. Then what happens to my x? So x, I'll get this as equal to minus 2. Then the second solution is that, so I can write this as s2 as equal to, so I'll get minus 2, 1 and 0. So those vectors, that is s1 and s2, lies on the plane of x plus 2y plus 3z equal to 0, which is the null space of A. And all the vectors on the plane are combinations of s1 and s2. Yes. So let us take one more example here to better understand. Let me save this page here. So let us take one more example here. So the question is that describe the null space of these three matrices. So we have three different matrices here, that is A is equal to 1, 2, 3 and 8, and we have B is equal to A and 2A, which is equal to, we have 1, 3, 2, 6, 2, 8, 4, 16, and C is equal to A with 2 times A in this form, so which is nothing but I'll get this as, so it's the same thing which is written, it is like a concatenation. B is a concatenation of A and 2A, and C is a concatenation the column wise A with 2A, so I'll get this as 1, 3, 2, 8, 2, 6, 4, 16. It's very simple. So now what the equation is that Ax equal to 0 has only the 0 solution, that is at x equal to 0, and the null space is z, that is 0. So if you look into the first case, that is for A, then we can write this as 1, 2, 3, 4, sorry, 1, 2, 3, 8 with my x1 and x2, which is equal to 0, 0. Then we will go with the same elimination process. We will multiply the row 1 with 3 times and then subtract with row 2. Then I'll get this as 1, 2, 0 and 2. So we got upper triangular matrix here. So we have x1 and x2. So if you go with this, what happens with the back substitution? So now the value of x2 is equal to 0. So when we substitute here in the first equation with the back substitution, then we will get x1 is 0. So ultimately the solution for this is equal to 0 itself. So here x1 and x2 both are equal to 0. So why? Because from this second pivot, if you see this, now what is my x2? The right hand side is 0, so I'll get x2 is equal to 0. So if I substitute in the first equation, that is x plus 2x2 which is equal to 0. So now x2 is 0. So here I'll get x1 is also equal to 0. So it means now I have the 0 vector here, and the solution is 0. So A is invertible, so there is no special case involved here. So this is one point which we have to note here. If A is invertible, whenever there is a invertible A, so then there is no special case exist. If A is invertible, then there are no special solutions, like how we have discussed for the previous one. So now let us take the C. Let us take this condition here, that is the C equation, and we'll see what do we get here. So let me redefine the C matrix here. So C is equal to 1, 2, let me write it neatly, 1, 2, 2, 4, 3, 8, 6, 16. You see this, it is not a square matrix, it is a rectangular matrix. Now if we try to eliminate the uh, its lower to the diagonal components or the coefficients, so what do we get? So how do we remove that? So here we have to remove this 3. So to remove this 3, I have to multiply with the same to row 1 and subtract with the row 2. So row 1 remains to be same, so it is 1, 2, 2 and 4. So what happens to the row 2 is that this will become 0. So now this is 3 2 is 6, so 8 minus 6, I'll get here 2, and here 3 2 is 6, so here I'll get this as 0. So here I'll get the so here 3 4 is 12, so 12 is minus 16, I'll get 4. So now if we see here, so this is my pivot, 1 is my pivot and 2 is my pivot. So whereas this 3 and 4 is not a pivot, so therefore it acts as a free column. So these two acts as let me take a different notation here. So these two acts as a different column here. So whereas these are my two pivot columns. So then what is the solution for this case? So let us write the solution here. So now so to understand this, we will write this in terms of a vector. So let me write this in terms of a column vector. So we have x1 here, so this is 1 0 plus, I'll write this x2 as 2 and 2 plus my x3 as 2 and 0 plus x4 as 4 and 4, which is equal to, we have 0 on the right side. We have 0 on the right side. Now it is fine. So now my third and fourth column are the free columns or the free variables. So whereas the first and second are the pivot columns. So I have to find out these. Now for these two, I will substitute randomly any of the value 0 or 1. So first let me take this 3 as 1 and the 4 as 0. So what do I get then? So for that case, I'll get here with x1 of 1 0 plus x2 equals 2 and 2. So since it becomes 0, so what do we have here? That x3, this entire thing will become 0. So I have this, so I'll send this to the right hand side. So since it is 1, so it will become minus of 2 and 0. So to get this right hand side, so what are the suitable values for x1 and x2? So if I substitute this x1 with minus 1, I'll get this right hand side with x2 equal to 0. So this is one of the special case. So I got the first special case, or the first special solution here is that, so if I define this, then my x1 is minus 1, x2 is 0, x3 is 1, and s4 is 0. So this is one of the solution. So what is the other solution? To obtain the other solution, so let me erase this. Let me delete this itself. And now I'll take, what I will do is that, now I'll change this variable values now. So now I'll substitute x3 with 0 and x4 with 1. Then we get here as x1 of 1 and 0 with plus x2. We'll get this as usual 2 and 2. So now what happens, this x3 will become 0, but we have x1, it is not 0. So that was a previous condition. So let me erase this. This is not a 0 condition. So then this is equal to minus of 4 and 4. So minus of 4 and 4. So how do I get minus of 4 and 4? So if I substitute x1 with 0 and then x2 with say minus 2, then I'll get the solution of the right side. So my second special matrix is that, or the second solution is that I'll get here x1 as 0, x2 as minus 2, and x3 as 0, and x4 as 1. So these are my the null space of C, the special solutions in the null space. So hope you understood this solution of null space. So let us define this in proper words and see the procedure in words. So let me save this here. So the procedure, it goes as follows. So let me write this in terms of points. So first one is that produce zeros above the it means now we are going beyond this next step. We are going to the next step here. So far what we have done, we have stopped only till the upper triangular matrix. So now we will go one step beyond this upper triangular matrix and get our the form of, see, whatever the matrix that you have seen before in the previous example. So there is nothing but, let me rewrite again. This may not be exactly the echelon form. Okay, so the previous example is a kind of echelon form where we don't have the pivots in all the columns. So now we will go one step forward and we will see the reduced echelon form. For that we have to produce zeros above the pivots by eliminating upwards. And the second point is produce ones in the pivots by dividing the whole row by its pivot. So we are going one step ahead of the previous example. We go one step forward with the previous example. So let us take the same previous example that we had discussed. I'll straight away write, okay, let me write the C and then I'll talk about. So we had in the previous example that a rectangular matrix, that is C, of form 1, 2, 2 and 4, and the second row was 3, 8, 6 and 16, and we brought this in a form by elimination process into a form like this. We had 1, 2, 2, 4, and the second row has become 0, 2, 0, 4. So this is actually called as a echelon matrix form. So I'll say this echelon matrix form later in detail. So it means that it doesn't have all the diagonals with pivots. So if you see, this is not a pivot, this is not a pivot. So we have the pivot here, So now we will go one step forward. Now this is in the the upper triangular form. Now we'll go one step ahead and we will eliminate the zeros above the diagonal. Now we will going to eliminate this above this diagonal, this 0. So to eliminate this 0, we'll go as usual the same method. So what I will do is that we'll multiply the row 2 with -1 and add with row 1. So then we will get this new form as, so this remains to be same as 1, so whereas this will become 0, so this will be 2 and this will become 0 here, and the second row will remain to be same, 0 to 0 4. So now what happened, so we have reduced this form. So now if you look into the diagonal, the diagonals are not in the form of identity. So to get this an identity, so we follow the second process, that is we divide by pivot itself. So if we divide by pivot itself, then anyway the first pivot is 1, so the first column remains to be the same, so we'll get this, whereas the second pivot is 2, so we'll divide this by 2, so here we'll get this as 1 0 and 2. So now we got the identity matrix. Now the pivot column contains identity matrix like this, and if you try to analyze this this reduced echelon form, we get the same thing. The solutions remains to be the same. The S1 and S2 will not going to be changed. So let us analyze just for our satisfaction. So we will write this as, again, that is x1 as 1 with 0 plus x2 with 0 and 1 plus x4, sorry, x3 as, what do we have is 2 and 0 plus x4 is, what do we have x4, that is 0 and 2. So 0 2 with the right side which is equal to 0. Let us try to solve this and find the special solution for this case. So as we all know that the pivots are exist only in the first column and the second column. So the third and fourth column is our free variable. So I can substitute this with 0 or 1. So let us take x3 as 1 and x4 as 0 in this case. So what do we get here is that, so I have x1 of 1 0 plus x2 as 0 1, so which is equal to, so what do I get here on the right side is that -2 and 0. So from this I'll get this -2 and 0 when I substitute this with -2, and here I have to substitute with 0. So I'll get one of the special solution is that is S1 is equal to, that is -2 0, here I'll get this as 1 and 0. So if you compare this with the previous solution, it is same as one of the previous solution. So now let us take the second case here. So the second case is that I'll substitute this x3 with 0 and x4 with 1. So what do we get on the right hand side is that, so let me erase this. So I'll get the right hand side as 0 and 2. So now to get this 0 and 2, what should be the value of x1 and x2? So the value of x1 and x2 is that, so this x1 remains to be 0 and here x2 should be -2. So now if you see this s2 is equal to that, this should be equal to what do we get here? So x1 will get 0, so x2 is -2 and x3 is 0 and x4 is 1. So this, even if we go one step ahead and we try to solve it, it means our solution did not change. The solution remains to be same. It means our null space solution is the same solution. So that is what we wanted to prove with this. So just to compare, we'll see the previous solution. Yes, it's perfectly the same solutions with respect to the previous case. Okay, then we'll stop at this point. So in the next tutorial we'll again talk about the same thing, and then we'll go for uh, the further with the echelon matrix. So thank you.